Today we're talking about different approaches in reinforcement learning for combinatorial optimization and reinforcement learning on graphs, and especially vehicle routing problems. And our first guest is Elias Khalil. And Elias, you can take it from here.
Thank you very much. I appreciate the invitation, and I'm happy to be joining you despite the fact that it's 7 a.m. for me. So I hope it'll be worth both of my time and yours. Okay, so since we have 3 talks on the same roughly the same topic, I thought I'd also spend some time giving kind of a big picture of this field, which I've been working in for a few years, and some of the challenges and recent developments there. And I will also, of course, talk about our NeurIPS 17 paper, Learning Combinatorial Optimization Algorithms over Graphs. And so I'd like to acknowledge my co-authors and colleagues. We've all kind of went our separate ways since, but yeah, I'd like to highlight my lead co-author, who's at Google Brain, and also another PhD student co-author at the time, Yu. And so our paper was published at the time at NeurIPS, and the code is available, and it's still kind of relatively widely used in follow-up work. So I invite you to kind of check it out and try to build on it or customize it to your problem if that interests you. Okay, so the overall problem setting revolves around answering this question. Can algorithms learn to design algorithms? The first kind is machine learning algorithms, which we see as general kind of tools for leveraging data in some kind of decision-making or prediction process. And the second kind of algorithms referred to as combinatorial or discrete optimization, and a couple of problems, real-world problems that are used to kind of motivate the wider importance of combinatorial optimization, which, depending on your background and what you do, may or may not be as apparent. So, I'd like to argue in terms of practical usability, optimization is, probably as widely usable as predictive modeling in some sense. And so here's one real-world problem that leverages combinatorial optimization that arises in the data center setting, where the data center receives a bunch of services or requests. So these are people or companies that need to use the servers for their workload, and they come in with some CPU and memory needs, highlighted by these bars and circles of different sizes. And the data center has a bunch of machines, and it might be a heterogeneous data center. So the machines might have different number of cores, memory capacities, etc. And the kind of the resource management problem asks for some kind of matching or assignment of services to machines. And so, and sorry for the dense slide, because I don't have animation here. It didn't really share well that way. But this is a mathematical formulation for this problem. So starting in the top left corner, we use variables to denote the decisions. And so XSM is the key variable. It says, it's a binary variable that is set to 1 if a service S is run on a machine M. And then if a machine M is being used at all by any one job, we also have a YM variable, which is set to 0 or 1. And we'd like to minimize, for example, the total number of machines being used. Okay, so the sum of the YMs. The constraints that you see at the bottom encode these operational constraints. For example, each service or job can run on one machine only, obviously. A machine is on if at least one job is assigned to it. And then for all machines, we need to respect the memory and processor capacity. We don't want to overload them. Now, of course, this is a simplified kind of illustration of this problem, but actually even even the real versions of this are not too far from what I just described. And so this is, this is a mathematical framework, combinatorial optimization, that allows you to describe formally such problems and potentially tackle them. Another recently kind of very interesting problem arises in the safety critical machine learning setting, which some of you may be familiar with, where people have identified that trained neural networks, say to classify stop signs or traffic signs more generally, might be very sensitive to small perturbations in the input that fool them into predicting the wrong thing. So for a stop sign, predicting that this is a yield sign rather than a stop sign. And if you think, if the network has, say, rectified linear units as nonlinearities, and you think of the neural net as a function f that takes some input and has some parameters, then you might want to do some computation to guarantee that a trained model has some kind of desirable behavior. And because rectified linear units are kind of discrete functions, they're stepwise linear functions, you can model them in a language very similar to what I just showed here, using binary variables and linear inequalities. And then you can solve like a verification problem that looks like this. Prove to me that there does not exist an input that is close to the original input such that the network or the model predicts incorrectly. So it's another kind of combinatorial problem. And more generally, these kinds of models or techniques have been used extremely widely in a very diverse range of applications over the last, I would say, 50 years. And as kind of computation and hardware picked up, we've only seen more and more applications. And so some of the notable ones include healthcare and energy systems. And one of the classical ones would be anything with airlines, basically. They've been using some form of combinatorial optimization to schedule crews and fleets for the last maybe 50 or 60 years for the many of them. And if you wanted to put a number on this, there's probably billions in savings and profit yearly. And this is based on a statistic from this Edelman Award, which is a very prestigious award for kind of industrial contributions to operations research. And there's kind of been an analysis of that, of the winners there and how much they have used discrete or combinatorial optimization. And so going back to the data center resource management problem, a common aspect is you don't solve this problem just once. You might solve the same kind of assignment problem, services to machines, many times a day. The frequency, of course, depends on the application. Here, we're simplifying and saying you solve this assignment problem maybe every hour. So you look at your new services, new requests, and you look at your machines which are up and available, and you try to solve the assignment problem. And so that forces us to kind of rethink the way we design algorithms for this kind of problem. Okay, so I'll make that more concrete. And so typically, in tackling NP-hard problems, there are three main approaches. Okay, let me see. I really want to share this slide because it has animations. Okay, that's impossible. Just give me 1 second. Okay, I think I figured it out. Okay, Vadim, do you see my full screen now?
Yes.
Okay, good, great. So I guess I'll just go full screen. Okay, good. And so how do we tackle these NP-hard problems? There are typically three paradigms that you can pick from. The first one is exhaustive search. I will not delve into that in detail during this talk. I'll touch a bit on what that means. But basically, many of discrete problems In the worst case, you can just enumerate all possible feasible, all possible solutions, say binary solutions. You can enumerate all 2 to the n of them if there's 2 to the n variables. And in designing such algorithms, this might sound crazy, but this is extremely widely used. You try to come up with tight mathematical formulations, and we have very powerful branch and bound solvers, actually exhaustive solvers, that can attack those problems. So this is the first paradigm if you care about global optimality. Okay. The other one is approximation algorithms, which you may be familiar with if you have a CS background. And there you don't hope for optimality, but you hope to prove a guarantee, a bound on the worst case quality of the solution that you return for any instance of the problem you care about. And last, if the first 2 approaches are too difficult or potentially uninteresting, then you can just design some kind of heuristic. You have some intuition about problem structure, and you try to tweak your algorithm to make it kind of work and exploit your intuition. Now, if you have multiple instances of the same problem, namely if you have data, then how do these 3 paradigms adapt to that? How do you tailor the algorithm to your set of instances? If you have exhaustive search, you try to come up with some problem-specific bounding functions or search rules, way to prune out the search space that leverages some specific knowledge about the instances you have. If you're doing approximations, you might assume that your certain parameters of the data come from some Gaussian distribution or some kind of well-behaved distribution, and then you can redesign the approximation to exploit some kind of distributional knowledge. And then you say, the approximation guarantee is something with some expectation. Last, for heuristics, what we typically do, this is, I would argue, the most common approach, is you have a bunch of instances in your application or in your domain, and you keep running this algorithm, you keep tweaking stuff with it, and you look for patterns. You notice that some parameter slows things down, so you switch it off or something like that. But in all of these cases, the answer is you need quite a bit of manual, intellectual, or experimental effort, and most of the time you need a combination of the 2. So this is not very highly desirable. You need quite a high level of skill to be able to do this tailoring process. And so this is the opportunity kind of to automatically tailor algorithms to a family of instances. And because combinatorial optimization or integer optimization are very widely used paradigms, there's a ton of problems that fit within those. This creates this big opportunity for improving lots of domains, lots of downstream applications in kind of unified ways. Okay. Now, in that direction, the first thing one might think to do is to do hyperparameter tuning of existing algorithms, right? So everybody here is talking about reinforcement learning. You know how critical it is to tune the hyperparameters of your training procedure, or your function approximation network, or what have you. So one can think about doing the same. Just as there are automated hyperparameter tuning methods for machine learning, why not do automated hyperparameter tuning for your optimization algorithms? So this is a screenshot of the solver Cplex documentation. So this is a very widely used integer programming solver, very effective. And it has a very wide list of parameters. So here MIP is mixed integer programming, this general paradigm for combinatorial optimization. And there's like a few hundred of these different parameters, different strategies. And each of them has a bunch of possible value, a range of possible values. And so, this is 2 examples of that. And then what you can do is say, why can I not apply hyperparameter tuning, just as I do with my machine learning models, to this algorithm, right? That's a plausible approach. And this is indeed a common approach that exists. And so if you've used, for example, the hyperparameter configuration software SMAC, this software was originally also used on optimization solvers. And so what you do there is you start with some parameter starting values, and then you keep calling the solver on your training instances. You observe some solution cost or some performance metric, and then you try to search for configurations which are potentially better. So it's a kind of a black box optimization approach. It is very easily applicable to many different problems. It's kind of very hands-off. You only need to do very little programming to get it to work. But the limitation is it operates at the instance level. You know, hyperparameter tuning doesn't look inside the algorithm, just tweaks high-level stuff and hopes that the algorithm works better. So it doesn't operate at the algorithm iteration level, and it assumes that the hyperparameter space that this human has designed for the algorithm is rich enough to express a wide range of versions of the algorithms that makes it adapt well to your specific set of instances. And so in that way, the solution is not necessarily satisfactory. Okay, so towards more of what we're going to talk about today, I thought we can warm up by thinking about learning within gradient descent rather within combinatorial optimization, first within continuous optimization. So this is a very nice illustration from Khalil at the time at Berkeley, who wrote this paper with Jitendra Malik on learning to optimize in the case of neural networks or continuous optimization a few years ago. The kind of the story goes as like this. You're optimizing some function with gradient descent. The ball is where you're currently your iterate is at, and you know, we can all clearly see like there's an optimal solution somewhere here, but following the gradient leads to some kind of oscillation, right? So you know, maybe this is the right direction, maybe not, but you can imagine if you have a non-convex function that just following the gradient as is, it might not necessarily be the right thing, or you might think that maybe the learning rate needs to be tuned in some intelligent way so that the convergence behavior is better. And so the learned optimizer version will ideally do the following. When it starts oscillating, it figures out that in the past it has seen a similar loss or objective landscape, and it will recall that it took a few specific steps to get out of this oscillation, and it will do that and converge faster. That's kind of the high level of intuition of what we would like to achieve when we apply learning to algorithms. And more specifically, if you look at general iterative optimization algorithms, you start at some random point, and then you iteratively compute some direction of change, and then you update your iterate by adding to it this vector, this direction. Typical gradient descent will tell you to take, you know, negative of learning rate times gradient at that point, but maybe a learned algorithm will be a neural net that looks at all the history of the past iterates that you've been at and come up with a different direction. It might also use the gradient itself, but essentially this is somehow tailoring the optimization procedure to the domain or to the instances. So moving on to combinatorial optimization problems, I'll use this minimum vertex cover problem to illustrate the setting. So in minimum vertex cover, you're given an undirected, in this case for simplicity, unweighted graph, and you would like to pick a subset of the vertices or the nodes such that each edge has at least one of its endpoints in the set that you pick, okay? So a common kind of toy application of this is, you know, social networks. You want to advertise something and you want to show it to only very few people, but you want it to spread eventually to many of them. And so you want to find the smallest such set. There's a greedy algorithm that guarantees that you will find a set that is a 2 approximation. So if the optimal solution has size k vertices, this will find a solution of at most 2k vertices every time. And what that 2 approximation greedy algorithm does is it adds at every step the 2 vertices that have the maximum sum of degrees. So for example, in this graph, if you look at these 2 nodes that I've highlighted with a green check, you'll see they have very high degrees. One of them is connected to 6, the other is connected to 3, 6 plus 3, 9. So these 2 have the highest degree, so I add basically the 2 nodes here. Now, in the next iteration, you only consider edges that are not covered. And so all the edges that are connected to one of the two selected nodes are considered covered. We're done with them. And you repeat that, and you get something which is at most 2 times bigger than the optimal vertex cover. Okay, so interesting, easy to implement algorithm with some nice guarantees. However, in practice, you may not be satisfied with a 2 approximation. So this is the point. This is where kind of learning starts to come in. And so the setting that we pose is the following. We're given some graph optimization problem G, a distribution D over problem instances, and we would like to learn better greedy heuristics that once trained on the training set will generalize to unseen instances coming from the same distribution. Okay, so this is the typical kind of empirical risk minimization setting in machine learning. The distribution D, think of it as graphs that are somewhat similar. They're coming from same distribution. So here I'm trying to illustrate, you have a same graph, and then maybe some edges come in, some nodes come out, some edges come out, etc. So it's a small variation on some base graph. And so the optimization instances are somewhat similar. They're somewhat well behaved. So that's one of the key assumptions here in terms of learning. So the first machine learning approach to think about most of the time is, can I turn this problem into supervised learning, right? So here's one way you can do that. You want to have a model that does the following. Given a partial solution, so what's a partial solution? Let's say in the bottom right here, I'm solving this vertex cover problem again, and I'm at iteration 3, and in iterations 1 and 2, I have picked the 2 nodes in blue. So that would be my partial solution, right? It's not a complete solution because not all edges have at least 1 node in the vertex set in the partial solution, but it's still a partial solution. So now what I want is a model that can predict the next vertex. So I have that in green. I'm using these green bars to denote some kind of score. And so you could potentially collect a data set where you have pairs of partial solution and next vertex. So that would form like the feature label pair. And the next vertex would come from some optimal solution to the problem. So maybe you run CPLEX, this integer programming solver, on the instance because it's a training instance. You get an optimal solution, and you use that to build a supervised data set. And this is indeed very close to what Vinyas et al. Did in Europe's 2015, where they introduced these pointer networks to achieve this. And so they said is, you have an instance P, you have a desired output CP, and what you want to do is get some parameter of this recurrent neural network, this so-called pointer network, to maximize the probability of generating the solution that we have in our database. Okay, so you want to maximize typical kind of objective, maximize the probability of outputting the right solution given the training instance and the parameters of the model. Now, an issue with that is because it's a supervised problem, you need to compute good optimal solutions to an NP-hard problem in order to be able to learn. So it's a bit of a chicken and egg situation. You're trying to learn a good heuristic for an NP-hard problem, but you need a good heuristic to be able to set up your learning task. So this can be a limitation in some cases where finding optimal solutions is just very hard. And so reinforcement learning kind of arose as a natural solution to this dilemma. And it didn't actually arise, in the last few years with our works, etc. This is relatively well established. So in 1995, Zhang and Dietrich designed this reinforcement learning approach to job shop scheduling. Job shop scheduling is a very, very famous type of scheduling problem where you have many tasks and many workers and deadlines and all kinds of dependencies in which job 1 must be completed before job 2, etc. And they were actually looking at this in the context of NASA space shuttle processing. They wanted to design a fast heuristic to solve this problem, and they did reinforcement learning in that, and they even had, if I remember correctly, like a small neural net as the function approximator. And so this idea of using reinforcement learning instead of supervised learning to derive tailored combinatorial heuristic is not new. And so we took inspiration not only from this paper, but also around the same time on arXiv, there was this also famous paper, Neural Combinatorial Optimization with Reinforcement Learning, that said you can use the same model from this paper, from Vinyals et al., the pointer network, but instead of training it with supervision, why not training it with reinforcement learning? The only caveat there was that they were not exploiting the graph structure of the combinatorial problems, which is something at the same time we were focusing on. And so again, our setting looks as this. We're given some graph problem. This is the first row in the table. And a family of graphs, maybe coming from some application. This is the second row. And we can do some kind of greedy operation in an algorithm. And we would like to learn the best way to make these greedy decisions. And this idea applies quite broadly to combinatorial problems on graph. And we, in our paper, we looked at actually 4 of them. These are 3 of them. The most famous being kind of the traveling salesman problem, which Reza and Wouter will talk more about because they worked on TSP and its generalization in VRP. And so what's the reinforcement learning setting then? We think of the greedy algorithm and the reinforcement learning setting, and we're trying to establish a mapping between the two. So in the greedy algorithm, a partial solution is very similar to the notion of a state in RL. The scoring function in a greedy algorithm, say, edges with the largest degree, is very similar to the Q function in reinforcement learning. It gives you some estimate of the goodness of a given action in your action space. And the greedy algorithm, what it does is at every iteration, it selects the best node according to the scoring function. The best node is very similar to the greedy policy. Okay, I realize my video is off. Sorry about that. And the greedy algorithm, all it does is says, until all edges are covered in the vertex cover case, you do 3 things. You compute scores, you select the best node with respect to scores, and then you add that node to your partial solution. You keep doing that until you solve the problem. So this is very similar to how an episode in reinforcement learning unfolds, right? So this is the first kind of connection to make. Now, the second challenge besides learning is representation. You want some features that will allow you to say, oh, this is a good action, this is a bad action. And so in our case, we were using the Q-learning framework. And so we were thinking about action value function, Q hat of the form. Q hat takes the current state and a given vertex, which is not in the solution. It has a bunch of parameters that regulate its behavior. And the Q function tries to estimate the goodness of a vertex in a given state. And what you want is you want some kind of representation of the nodes, V, some vector that says something about them. You could do feature engineering, but as always with feature engineering, if you move from vertex cover to TSP to max cut, it's unclear that the same features are very useful in different problems. And so it's very difficult to generalize these ideas across different problems and different graph sizes. And so the other key thing we did was to leverage the kind of representative or expressive power of graph neural networks, which allow some kind of nonlinear message passing between the nodes of a graph that enables some potentially useful representations. And this allows you to avoid the need for feature engineering. And of course, the parameters of this graph neural net are trained jointly with the policy. And the graph neural networks are also invariant to graph size. So you can train this model to work on a graph with 100 nodes and then test it on much larger graphs potentially. So briefly, graph neural nets, generally the way they work is they do some kind of message passing between the node. So this is an illustration from a recent survey that we put out on this topic of using graph neural nets for combinatorial optimization reasoning, and also talks a bit about reinforcement learning in that setting. Basically, what the graph neural nets are going to do is they're going to look at the neighborhood of a node, say the node V4. It's connected to V2 and V5, and it's also connected to itself. And so in every iteration of this embedding process, it'll receive messages from its neighbors, do some kind of nonlinear mapping of the messages it receives, and somehow aggregate them or merge them. And this gives you a new vector for that node. And you want to train the parameters of this complicated neural net so that they give you some good output. In our case, the good output will be the typical kind of, regressing on the Q value. And so the overall, yes.
Are these networks then trained with fixed point iterations that we keep passing the messages until they stop changing?
That's a great question. So it depends on the specific kind of architecture that you pick. In our case, we were using one that my co-author Henjun Dai had designed called Structure2Vec. And in that case, we were not doing fixed point iterations. We just had a fixed iteration parameter, which was something between 3 and 5, because otherwise it gets complicated with gradients and kind of computational numerical issues. Yeah. So the overall approach for doing Q-learning, for learning the greedy algorithm, and this might be, so pseudocode might be very familiar to you. And I'll go on the right side here. You have some model parameters which you want to learn. What you do is iteratively, you sample a graph problem instance, you explore or exploit according to your current policy, and then you update your state. Then based on that, you all can also have, some experience replay, etc. But the main step is the typical kind of regression update, gradient descent update in Q-learning, where you try to, update the parameters theta of your model to match the actual observed reward more closely. Okay, and then you keep doing that until you somehow reach some convergence criteria where you're not able to improve the reward by much. Okay, and so the overall framework looks something like this. A graph comes in for some combinatorial problems. This big rectangular box is essentially the graph neural network embedding, which is trying to combine these boxes, these vectors of the different nodes, and it turns them into scores, these green bars, and then a greedy policy will add the node with the highest score. In this case, it's this node, and that's our first iteration. Now, this is our current partial solution. We move to iteration 2, starting, assuming that we've already picked this node that is in yellow, and we repeat the same embedding process, picking the second node. For this simple graph, this instance of vertex cover is solved, right? But the idea is generally applicable to graph problems doing similar kinds of manipulations. And so without going into too much detail, these results have been kind of improved on, and the speakers after me will talk a bit about improvements they've made. But even at the time, we could see that our method, which is the smallest bar here, was achieving an approximation ratio that is very close to 1. So 1 means you're close to optimal for vertex cover, max cut, and TSP. And this is compared to a wide range of learning and non-learning based heuristics for these different combinatorial problems. And again, the code is available, so please, you're welcome to use it and try to build on it. And
wait, some of the 1 is supposed to be the best ratio, right? Then in these results, the less the better. Am I correct?
Exactly. Yes. Yes, indeed. And so we've observed that this learned strategy tends to find interesting heuristics sometimes. So this GIF will repeat. But this is solving a vertex cover on a graph, learn the heuristic with this method I described versus a classical greedy heuristic on the right. And the one that finishes the graph first is the one that found a smaller vertex cover. So finishing earlier is better. You'll see the learn heuristic is struggling. It seems like it has a denser graph, but at some point it picks up and then it solves the instance here. And what it's doing, apparently visually at least, is that it tries to maintain a big connected component. And a big connected component is easy to break up by picking one node of it, because there will be a lot of connections within the same component. The classical heuristic breaks up the graph into many disjoint parts. It becomes harder to cover the edges there. And so we've also observed some interesting strategies naturally arise from the training. And so as a takeaway, reinforcement learning is very useful here in tailoring greedy search to your specific instances, learning features jointly end-to-end with the greedy policy. So the graph neural net parameters and the policy. And the human priors, our understanding of algorithmic search is encoded by saying we want a greedy procedure. So we're not searching in an arbitrary space of algorithms. And interesting novel strategies can emerge from that. And so to answer this question I posed earlier, yes, machine learning can help tailor combinatorial optimization algorithms to your instances by complementing some of the human algorithms using data. So this is really kind of the main power of ML here in this context. And going beyond heuristics, if you're not satisfied with just a heuristic, you want optimal solutions, you have to go to exact solvers. This is a plot showing the speedups for one of the exact solvers, Gurobi. So these are very widely used really in industry, probably as used as standard heuristics. And so I wanted to just plug work by some colleagues of mine that have designed a reinforcement learning library that's like OpenAI Gym, but for learning within integer programming solvers, particularly the skip solver, which is an open source solver hosted in Berlin at the Swiss Institute at ZIB. And so they have this out on GitHub, open source, very useful if you want to experiment with reinforcement learning for exact solvers for integer programming. And this kind of line of work that I've worked on in my PhD has had quite a few extensions and applications in various domains. And some of the most notable kind of follow-up works are the two from the two speakers that are gonna speak next. So definitely looking forward to that. And we've had a tutorial last month at AAAI, which is a very extensive 3-hour tutorial on integration of ML and combinatorial optimization. So I invite you to check out this website. All the materials and the recording are available there, and there's much more detail than what I was able to cover. We've also been running this discrete optimization talks seminar, and we have a YouTube channel, and a few of the talks have covered the intersection of machine learning and combinatorial optimization. So if you're interested, you might want to check that out. And with that, I'd like to thank you for your attention. And here are some relevant papers in this space that I'd like to advertise. Thank you.
Thank you very much. Thank you for joining us at this early hour.
Yes,
you really did make it sound, make your solution sound like really natural, like it flows out of the problem. Hopefully, we can get your slides somehow, because you have many great links, especially slide 36 with all of those data.
Yes, I will get you a PDF of the slides, no problem.
Great. So does anyone have questions? I have a couple, but I would like to go last. So. Yeah, then I will start, I guess.
Sure.
Wait, do we have a message? Oh, no. So you mentioned human heuristics there, but how do you do you do something to incorporate prior heuristics into how the learned heuristic solves the problem? Do you pre-train on prior heuristics or something?
So that's an interesting situation. So here what I was trying to say is the greedy algorithm itself can be seen as like a prior, because it says you only need to score every possible action, once at every step and incrementally add them, rather than say at every iteration, look at a combination of possible actions. So in a way, greedy here is the prior. But in this survey that I'm plugging here, this one, which is just out, there's actually this evolving field of algorithmic reasoning that Petar Veličković is focusing on at DeepMind in London, where it's something more like what you're saying there. So if you're trying to learn a shortest path type of algorithm, you know that there's the Bellman-Ford algorithm, and you know that the Bellman-Ford algorithm maintains some invariance at every iteration. So you try to train your neural net to kind of conserve the same behavior by having some kind of labels that that depend on the iterations, not just on the final output. And so this kind of thing of algorithmic reasoning or algorithmic alignment is a way to approach this encoding.
Thank you. Okay. I shall look at this paper. Also, I noticed on a lighter note that you're using social networks in your examples. Like, did this problem flow out of? Was it inspired by some social formulation?
Not really. I had worked on a similar social network problem a long time ago, and just Vertex cover is kind of connected to that. But I wouldn't say it's the biggest application. It's just one that I use to motivate Vertex cover. But I'm more interested in general kind of operational problems. I'm not really interested in web problems for that matter. Yeah.
Definitely. Okay. Thank you. I think we're a little bit late on time, but sure. Would be happy, I think, to take other questions if someone has them. Yeah. So there's. Do you see the chat?
Yes, I see the chat. I see Igor's question. Yeah, RL plus graphs. I think much more than social networks. Really, these kinds of applications in transportation and logistics have a huge potential there. So thinking about like ride sharing, where you have mobility network, traffic network, cities, etc., there's actually a lot of potential there. But getting data and kind of formulating a very high impact problem is a bit difficult if you're not in industry. But I would say like transportation is probably a huge one.
I think Schiphol Airport, that's really like close by to us, has been experimenting with those kind of solutions. I have seen papers on airplane schedule optimizations that use their data as basis.
Yes. And there's been some NeurIPS challenges doing multi-agent reinforcement learning for like managing trains, etc. So there was one last year. So that's, and I think the next two speakers are going to talk about these kind of routing problems in more detail. Yeah.
Okay. Thank you.
All right. Thank you very much, everyone. I'll unshare my screen here.
So can I ask one more question, maybe?
Sure.
So thanks for a very nice talk and a clear also overview of a bit of the background. So I was wondering if you can also comment a bit on like, I think this relates to the question before, like the prior knowledge we put in terms of reward structure. So, because when I was looking into your paper, I find that actually for TSP, you're using like the flipped reward, which it lists somewhere. And I was wondering how does that tie into like?
That was a bit of a hack. That is a part of our paper that I don't actually like so much because it's kind of like reward shaping, reward engineering to try to get something to work to some extent. Since then, I have become a bit more, not to say skeptical, but careful in thinking about how to approach this aspect of using rewards. And honestly, in the space of like heuristic algorithms, I see less and less room for doing something that is extremely effective with learning in a kind of hands-off way. I think our papers were like good for their time because they introduced this different ideas of approaching algorithm designs when you have data. But I think generally like there's not too much that can be done beyond that with better reward shaping. The only interesting avenue I see is this kind of algorithmic alignment, which potentially infuses a lot more knowledge in the policy being learned by giving it lots of like partial signals along the way. So that's kind of,
Okay.
But I'm happy to discuss this more later on for sure.
Okay, yeah, thanks.
All right.
Thank you. The presentation.